let's talk about a fatigue example where we can go through virtually everything we're doing in our machine design course related to fatigue. So we have this stepped cantilevered machine cylindrical steel bar with a larger diameter of 2 inches. So that would be this portion here, and a smaller diameter of 1 inch. So that would be that portion there. It's to be placed in a situation loaded with a transverse load varying between 100 and 500 pounds in an environment of 700 degrees Fahrenheit, using AST minimum properties and a reliability for the endurance limit estimate of 99.9%. We need to estimate the endurance limit, and using the Goodman criteria, determine the safety factor for infinite life. If we can't rate this for an infinite life, we need to determine the number of cycles that we could safely rate it for. We know that the ultimate strength at room temperature is 150 kpsi. My first step is going to be calculating the new ultimate strength based on this elevated operating temperature. So to do that, we can use this equation here, this ST over RT, and we can plug in our temperature there. So we'd have 0.98 plus 3.5 times 10 to the minus 4 times 700, and that will be minus 6.3 times 10 to the minus 7 times 700 squared. And now that will equal our ST. Our ST over RT is going to be equal to 0.91. So our new estimate for the ultimate strength is going to be 0.91 times our ultimate strength at room temperature, so 150 kpsi, and that will give us a new estimate of 137.44 kpsi for our new ultimate strength at that elevated temperature. The next thing we'll want to determine is our estimate for our endurance strength. So this is the SE prime. And to do that, we will just take our ultimate strength and divide it by 2. So we would have a new estimate for, next we will need to get an estimate for our new endurance strength, our unmodified endurance strength, and to do that, we will take this new ultimate strength, 137.44, and divide it by 2. And that would give us an estimate for this unmodified endurance strength of 68.72 kpsi. Now this is our unmodified estimate for the endurance strength, and so now we need to use our Marin factors to get an estimate for our endurance strength at these given conditions. So the first one that we'll do is Ka, which is our surface factor. So to do that, we can go to this figure over here on the right, and we know that our ultimate strength is at 137, so we're going to be right before this 140, and we have a machined part there, so we're going to call this 0.704 Ka. For our Kb, which is our size factor, so we have a cylindrical bar and it is not rotating. So we need to use this effective diameter for something that's not rotating. So to get an effective diameter, we have our effective diameter is going to be equal to 0.370 times our diameter, which is just 1 inch here. We're going to be looking at our critical location is right here where the smaller portion meets the larger portion. And so we would have our effective diameter is equal to 0.370. And now we will plug that into our Kb equation here. And so we would end up with our effective diameter is 0.370. So we can use this one right here. And so we'd have our KB is going to be equal to 0.879 times our effective diameter of 0.370, all to the negative 0.107. And that will be equal to 0.98. So we have our Ka and we have our Kb. We know that our Kc, which is the load factor, will just be equal to 1 because we are in bending. Our Kd is going to be equal to 1 because we already took care of the temperature effect when we did our new ultimate strength, and now we need to figure out what Ke is, which is our reliability factor. We see here in the problem statement that we have a reliability of 99.9%. So we come to this table and we can find that Ke is going to be equal to 0.753. So now to get our estimate for our endurance strength, we will have Se is going to be equal to Se prime times Ka times Kb times Ke. So that will be equal to 137.44 times our Ka, which was 0.7, times Kb, which was 0.98, times 0.753. And if we do all that, we will end up with an estimate for our endurance strength of 35.41 kpsi. Now we know that if we are doing our Goodman criteria, we know that we need the alternating stress, the mean stress, we need the endurance strength, and the ultimate strength. So we now have 2 out of 4 values. Now we need to understand what our alternating and our mean stresses are. And one thing we have to do there is take into account this stress concentration due to this radius there where the 2 different diameters are meeting. So to do that, we find the appropriate stress concentration table. Here we would be looking at our D, our larger diameter over our smaller diameter is going to be equal to 2, so we'll be somewhere in between these two. And our fillet radius over our smaller diameter is going to be equal to 0.1. So we would be somewhere right in here. So our KT is going to be equal to 1.75. And to calculate Q, which is our notch sensitivity, we will need to find our notch radius, which is 0.1 inches, and come up here to find our notch sensitivity, and that will be equal to 0.87. So now to find our fatigue stress concentration, we can use this equation of Kf is equal to 1 plus Q, which was 0.87, times our static stress concentration, which was 1.75, minus 1. And our Kf then will be equal to 1.65. That makes sense here. Our fatigue stress concentration should always be less than the static stress concentration factor. So now we have our stress concentration. We need to find what our stresses are. So first we'll look at our minimum stress. So this stress is due to bending. So we would have sigma is equal to mc over I. So here our moment for the minimum would be 100 pounds times a distance of 10 inches, and our C is going to be equal to half our diameter or equal to our radius, so that will be 0.5 inches. All over I, which is pi d to the 4th, our d is 1 to the 4th, all over 64. So that will be equal to about 10.2 kpsi. Our sigma max is going to be equal to 500 is our maximum force there. We'll have the same moment arm of 10 inches, the same C of 0.5 inches, and that will be over our pi times the diameter. So 1 to the 4th over 64. And that will be equal to 50.9 kpsi. Now our alternating stress, so we want to go from our maximum, our sigma max, minus our sigma min. So we're trying to figure out the distance between those two, and we divide it by 2 and take the absolute value of that, which gives us our sigma A is going to be equal to, and I forgot here, we want to multiply that by Kf. So our sigma A is going to be equal to 33.7 kpsi. And our mean, we want to do Kf. And here we're going to have sigma max plus sigma min all over 2. And so our mean stress is going to be equal to 50.5 kp. Okay, so now we will have all the values we need to look at our Goodman criterion. So we have our endurance strength, we have our alternating stress, our mean stress, and our ultimate strength. So our fatigue factor of safety here is going to be equal to sigma A, so our alternating stress, so 33.6, all over the endurance strength, which was 35.41, plus our mean stress, which was 50.5 kpsi, all over the ultimate strength, which was 137.45 kpsi. And if we do that calculation, we end up with our n is equal to 0.76 or 0.8 if we're just taking to the 10th place. Now, since this is less than 1, we know that we cannot rate this for an infinite life. So since it is less than 1, the problem asks us to estimate how many cycles we can rate this for. Now, to do that, we need to get an equivalent fully reversed stress, which is this sigma AR, so the alternating stress, and we're indicating with the R that it is reversed. So here we can have our sigma A, which was 33.6 kpsi, all over 1 minus our sigma, so our mean stress, which was 50.5 kpsi, all over our ultimate strength, which was 137.45. And that will equal 53. So our sigma AR is going to be equal to 53.2 kpsi. So if we have sigma AR is going to be equal to 53.2 kpsi, now we can estimate the number of cycles that we can rate this for. And to do that, we're going to need this equation here. So we need the A and the B, and then we can plug those in there to get this estimate for the number of cycles. And first, we're going to need to figure out what our F value is for this equation. And to do that, we just need to come here to where our ultimate strength is. We come up to the curve, and we'll see there that our F is equal to 0.81. If we have F is equal to 0.81, then A we have here can be equal to 0.81 times our ultimate strength, which was 137.45 kpsi, and that will be squared all over the endurance strength, which is 35.41 kpsi. And so here I'm just going to include our 10 to the third to get to a base unit just to make sure our math works out correctly. And here for B, we'll have a negative 1/3 times the log of 0.81 times our SUT, which is 137.45 times 10 to the third, all over our endurance strength, which was 35.41 kpsi. So our A will be equal to 3.49 times 10 to the fifth. Our B is going to be equal to a negative 0.17. And we can plug this in here. So we would have the number of cycles that we can rate this for is going to be equal to our fully reversed equivalent stress. So we'd have 53.22 kpsi. That's all over our A, which was, and we'll include the 10 to the third here, and we have 3.49 times 10 to the fifth, all over 1 over a negative 0.17. And that will be equal to 85,780 cycles, or we just say 85,000 cycles, because we don't want to give the impression that we know our number of cycles that we can rate this to with that much precision. So I will usually go down to the next round number there. So we can rate this part for 85,000 cycles.